Let me give you another example. There are atomic clocks that are accurate to better than 1 second in a million years. There's one of these located at the National Institute of Standards and Technology at Boulder, Colorado. There's an identical clock, virtually identical clock, at the Royal Observatory at Greenwich, England. Both these are very elaborate scientific devices that are incredibly accurate. They're accurate to better than 1 second per million years. And I'm always reminded whenever I encounter this, when I was on the board of a company that was acquiring a company that made cesium clocks in Boston. When we were in this acquisition, the proud president was presenting to our board the fact that they made these clocks that are this accurate. And I said, I only have two questions as an acquiring director. How do you know, and who cares? Well, the way you know is from the resonance of the cesium atom, and I won't go into that all here. But as who cares, the accuracy of your ability to, the accuracy of your measurement of time determines the accuracy of your navigation. And these clocks, this kind of clock, makes the global positioning satellite system possible. But the point is, these two super clocks in Boulder, Colorado, and at Greenwich, England, are differing every year by 5 microseconds. The one at Boulder is 5 microseconds a year faster than the identical clock at Greenwich. The question is, which one is correct? And the answer is they both are. The clocks are not inaccurate. Time is different. You see, in Boulder, Colorado, is at 5,400 feet altitude above sea level. In Greenwich, England, it's 80 foot above sea level. And time is actually different at those two places because of a difference in gravity, among other things. These atomic clocks, if I had an atomic clock here on the platform and raised it 1 meter, it would speed up by 1 part in 10 to the 16th. In other words, 10 with 16 zeros after it. Not much, not enough to change your schedule, but it's predictable and it is measurable. And they actually did this. They sent aircraft around the world, eastward, with such a clock, and one at rest at the observatory. They also sent one around the world westward. And they gained and lost exactly what Einstein's theory would have predicted due to the relative motions and so forth. But another example that perhaps will get this across, if you read a physics textbook in this area, they almost always talk about two hypothetical astronauts. And we're going to leave one right here, and we're going to send the other one to the nearest star. If you go out to the night sky, there is a star called Alpha Centauri. It's 4.5 light years away. Light years a measurement of distance. And we're going to send one of these imaginary astronauts to Alpha Centauri and back. Well, Alpha Centauri is 4.5 light years away. So if we send him there at half the speed of light, it'll take 9 years to get there and 9 years to come back. It's an 18-year deal. That's on Earth time. If he takes a clock with him, he'll discover something strange. On his clock, because of the travel and so forth, will speed at a different rate. And since he's traveling at 50% of the speed of light, you can apply the Lorentz transformations to make that correction. And you'll discover that when he gets back, he will end up being 2 years, 5 months younger than his twin brother. Here are two astronauts born at the same instant. One goes on this trip, and when he gets back, he'll be more than 2 years younger than his twin brother. And if that doesn't bother you, you weren't listening carefully. This is an example of what we call the dilation of time. Time is a physical property. It varies just as length, mass, and other things vary due to Einstein's theory of relativity.